Hey again, everybody. We are jumping into lesson 1.4 now, and there's going to be two different videos for this lesson. This one is going to focus more on previous chemistry content and concepts that were from grade 9 chemistry unit and grade 10 chemistry units. So it would be a great idea to watch through this just to refresh if it's been a while, or you forget a lot of that stuff from grade 9 and 10, and it'll get you to a better spot where you'll be more more easily able to understand the new stuff that we get into for the 11 chemistry course, and that video will be coming out tomorrow. And so yeah, this is going to focus more on previous knowledge to get those caught up that might want to watch. So let's jump in. As usual, we've got our learning goals, success criteria here that we should understand by the time we finish lesson 1.4. And so some stuff that was covered in previous courses: chemical compounds. Generally, there's two kinds of compounds that we should be aware of at this point: ionic compounds and molecular compounds. And they each have different physical and chemical properties. And you might remember that you learned previously that ionic compounds are made of a metal with a nonmetal, or at least something positive, some kind of positive ion bonded to a negative ion. But molecular is different because it consists of only non-metal elements. So it could be two or even more than two nonmetals bonded together. There's more differences, but we won't worry too much about those quite yet. But let's keep going. Ion. So this is one of the big focuses of this slideshow, the concept of ions. So we'll go through that. We've touched on it a little bit in the course already, but we'll get into like the details of how ions form and why, and the different kinds of ions. But generally, an ion is just an atom. It could be just one atom, or it could be a collection of atoms together that either has a positive or a negative charge assigned to it. So how do we form an ion? Well, we have to either gain more electrons, which will make the atom more stable, or we can lose electrons for the same reason, to become more stable. And the idea here is the valence shell, or the valence ring of electrons, we want to either fill up, so that's typically 8 electrons, and that's called a stable octet. Which is 8 electrons. Or to become an ion, you can also lose electrons so that you're essentially emptying out the electrons you have in your valence shell. So that becomes empty, and then the next one inside it is already filled up, so you're left with that one being the full valence shell now, because that's now the outer one. So that's generally why ions are created, is to make the atom more stable in terms of energy. Things are always preferred to be in a lower energy state than a higher one in nature, so ions are a way of doing that in chemistry. So let's look at creating a positive ion first, and we'll look at sodium. So we know sodium is in group 1 of the periodic table, and we also know that it has 1 valence electron, and you can see that in the picture here. So if sodium wants to make itself a little bit more stable, well, it could try and collect 7 more electrons to add to that valence ring to give it 8. But that would be really physically probably impossible. It's much easier for sodium just to say, well, I only have one in my valence ring. Let me try and get rid of that one electron, and that will leave the next ring in to become the valence ring, and that's already full. That will make sodium more stable. So if that electron right there gets taken away by something else, sodium's able to lose it, then it's going to lose one negative charge, right? One electron is one negative charge. And so it turns into sodium plus, has a +1 charge. It's now an ion. And so we write a square bracket anytime we're drawing diagrams of atoms that have become ions. We want to put square brackets around it, and we also indicate the charge by writing that in the outside the square brackets, just up in the top corner. So that would represent sodium +1, and it's a +1 ion because it had just one electron that it wanted to get rid of to empty out that valence shell. So the plus symbol is written as a superscript, and that indicates that sodium has a charge of +1, meaning it has one extra proton now than electron, so one extra positive thing compared to the negative things. So let's look at a negative ion. How does that form? We're going to go all the way across the table to chlorine now, and it's in group 17, so that tells us that the last shell, or the valence shell, of chlorine has 7 electrons as a neutral atom. And to become more stable, chlorine would love to get one more electron to bring it up to 8 and fill out that outside electron shell. That would make chlorine more stable. So if it can find or pull away an electron from something else and fill up, that's going to make it more stable. It's also going to turn it into an ion, and it will become a negative ion, charge of -1, because it has collected one extra negative electron. And so we can see that this was the empty spot here where the electron could be added, and if the chlorine can collect it from somewhere, then it will fit into that spot, and we now have Cl negative. So we've got our atomic drawing here. We put our square brackets around that, and we say this is a charge of 1- for chlorine. So pretty simple ideas here. We're going to see this pattern develop where we've got everything over on the left side of the table. The metals in group 1 and 2 always want to lose electrons, and they will become positive ions because they only have a couple, 1 or 2 electrons in their valence shell. And then the ones over on the right side of the table are getting close to filling their valence electrons or valence shell, so they almost always add 1 or 2 or 3 extra electrons to fill their valence, and that's going to make those elements always negatively charged ions. So there we have the summary for chlorine 1-. Okay, so we've made a sodium ion and a chlorine ion, and there they are. Both ions now have a full valence shell containing the maximum number of electrons possible. So this one's drawn here because there was an electron in there before, but you typically wouldn't draw that when you would do your diagrams because it's empty, and we don't really draw empty electron rings, but it's dotted because it's showing you that it did have one and it lost it, so now it's the one inside that's the valence shell and it's full. And then we've also got chlorine here, which added 1 to fill its valence shell. So we've got a +1 ion and a -1 ion, and these two ions are now in a more stable state energetically. And that's why ions form, to make the atoms into basically a lower energy state. So back to trends. We've seen this picture before. We've got kind of the center of our periodic table cut off, and we're just looking at elements 1 to 20 here. So we know the trend where everything in group 1 has 1 valence electron, and everything in group 2 has 2 valence electrons. 1 valence electron. And then over on the other side of the table, we've got 4 and 5 and 6 and 7 and 8 valence electrons, because the group number tells us how many they have. So if we consider that 8 is a full octet, 8 is the amount that we want to have in the valence ring, and we know how many there are in the neutral atoms to start with, what groups do you think would want to gain electrons, and which ones do you think would want to lose electrons to become more stable and become ions? Well, I kind of answered that before we got to this slide, but here's the answer. Group 1 elements, since they have 1 valence, they always want to lose that 1 electron. It's really easy to lose 1 to become stable and empty out that valence shell, leaving the next one in full. And over on the other side, group 17 already has 7, and we've already seen the example of chlorine. If they all can gain 1 electron, then they will fill up their valence shell of electrons and become more stable. But that's not the only two groups that can gain and lose electrons. We can see that groups 1 and 2 and 13, so here, here, and here, it is numbered group 13, but it has only 3 valence electrons in there. It's easiest for them to lose electrons to become stable, because if you do the math, it's easier to lose 1, 2, or 3 than it is to try and collect and gain 5 more or 6 more or 7 more electrons just by comparing the value of the numbers themselves. And then group 15, 16, 17 on the other side of the table, they want to gain electrons to fill up their valence shell. And it makes sense because it's easier to try and collect 3 more or 2 more or 1 more electron than to try and lose the ones they already have, because they already have more than 4, right? It's more than half full already. So they're just going to try and continue collecting and fill up to become stable. So the general idea is on the left side of the table, those are metals, and they typically lose electrons to become stable and make positive ions. And on the right side of the table, you have nonmetals, and they typically try to gain electrons, which makes them negative ions when they become more stable. And we have skipped over group 18 here, and you probably know why. Those are the noble gases, and if you look at their valence shell, they're already full, right? Helium can only have 2 in its valence shell, so it's full. So they're all full. That means they don't need to gain or lose any electrons to get themselves more stable. They're already as stable as they can be, and everyone else, all the other elements on the table, are jealous of them because they don't have to gain or lose anything. They're already perfectly stable. So they don't really react much at all with other things. And that's the reason. They don't need to get more electrons or give them away to anything, so they don't really react. The other group we haven't talked about is group 14, which is the group with carbon in it. So that one, it's rare. It does happen, but it's really rare that carbon or silicon will lose 4 electrons or gain 4 electrons, because that's just a lot. Energetically and physically, that's not something that happens too often. But it is possible. It does happen from time to time, but group 14 we typically don't see involved in forming ions or in making up ionic compounds, because 4 is a lot to gain or lose. They generally are involved in covalent bonding molecular compounds, not ionic compounds. Okay, cation. That is talking about, that's the special name for positive ions. So if you're a +1, +2, +3 charge on your ion, that means you've given up some number of electrons and you're now positive. So that's called a cation, and you can think of a cat's eye if you want to remember that, I guess. Anion sounds similar to onion, and onions, when you cut them, make your eyes water, which makes you sad. And so you can think of that as a negative experience. So anions gain extra electrons, and so anion is the special term for negative ions. Keep an eye on your ions. Cations are positively charged. Anions with the N are negatively charged. So there you have it. All right, we're about halfway through already. Okay, noble gases. We just talked about them, but there's some pictures of what they look like when you send electricity through atoms of those noble gases, and they give out the different colors. So the neon lights, like I was saying in a previous video, neon lights are not just made of neon. They're made of all the different noble gases or combinations to get different blends of colors. And so these are what the colors are with the pure noble gases, each one of them. But they already have their full valence shell, and so that means they don't really create ions, they don't really react with anything. So when we do have other elements forming ions, the idea is that they are trying to get their electron number to be the same as the noble gas that they're closest to on the table, which will then mean that the ion and that noble gas have the exact same number of electrons. And we'll show you what that means. So let's look at sodium, magnesium, aluminum. So that's elements in group 1, 2, and 3. The closest noble gas to them is number 10 here, neon. And these elements are number 11, 12, and 13, so they come right after neon. So you should be able to tell me how many electrons neon has. If its atomic number is 10, it has 10 protons, and it has 10 electrons, right? So sodium, magnesium, and aluminum, if they create ions, we know that they lose electrons, so they're going to become positive, and the charge they get is dependent on how many electrons they lose. So sodium, we already saw, loses 1 because it has only 1 in the valence it's in group 1. Magnesium in group 2 loses 2, becomes 2 plus charge. Aluminum in group 13 has 3 valence, it loses all 3 to become a plus 3 ion charge. And the thing is, all 3 of those now have the exact same number of electrons, and it's the same number as neon, which is 10 electrons. You can count them up and double check if you want to, but they all have their first electron shell filled with 2 and their second electron shell filled with 8, which means that they all have 10 electrons. And you can see they all have the same electron arrangement now too. First shell filled, second shell filled, and that's that. So all 3 of these ions here, Na+, Mg 2+, and aluminum 3+, are all looking the same electronically as neon, which we know is very, very stable. So this is just a visual way of showing that when we create ions, they actually become isoelectronic is the term, which just means same number of electrons as the noble gas that they're closest to on the periodic table. And the same thing can be seen when we create anions with elements on the right side of the table. So we'll look at neon again, and the 3 elements that are closest to neon just before it are F, O, and N. So we know elements over on that side of the table want to gain electrons to fill up their valence shell. And Bohr diagrams, so let's see what we can do here with Bohr diagrams. So neon, well, I'm going to cheat, and I'm going to copy this and put it in here. So my Bohr diagram for neon is done. One thing I forgot though is, even though I said it earlier, these ions need their square brackets around them, right? Because they do have a charge on them. So aluminum, there we go. The neon doesn't need the square brackets because it's not an ion. And I will do nitrogen here, nitrogen, 2 rings, and of course it had 3, sorry, no, what am I doing? I'm thinking of the wrong side of the table here. It had 5 valence electrons in this second ring here, but it collected 3 more from somewhere, which brought it up to 10 electrons. And so nitrogen with a 3- charge now has the same number of electrons as neon, right? 10 and 10. And oxygen, same deal with oxygen. We've got, originally it had 6 in the valence, like this, and then it gained 2 electrons, which made it become a -2 ion to fill its valence shell. So it also has 10 there. And we'll finish things off with fluorine. 1 and 2, and originally it had 7 as a neutral atom, and if it found its 8th, then it filled its valence ring and gave it a 1- charge. So all of these have 10 valence electrons, right? And so they're all isoelectronic to neon, which is its closest noble gas. And making these ions for these three elements makes them more stable. All right, how to write symbols for ions. Well, we just write the symbol of the element and show the ion charge as a superscript to the top right of the element symbol. So calcium ion, Ca is the symbol, and a 2 plus in the top corner to show the charge of the ion. If an ion has simply a +1 or a -1 charge, you don't have to write the number 1. So Na plus is typically what is written, not Na1 plus. You're not going to get in trouble. I'm not going to tell the vice principal on you or anything like that. Not going to lose marks if you write the 1, but you don't have to, so you can save yourself that sliver of a calorie and not write the number 1. What about naming? How do we name an ion? Well, it depends on if it's positive or negative. So metals, we know, become positive, and a metal that lost electrons to become an ion just has the same name as its element. So Ca+2 is just called a calcium ion. Calcium is the name of the element. And I should put my square brackets around there and say the charge, because that is a 2 plus calcium ion. Anions are a little different. So if we've gained electrons and we've become a negative ion, we change the ending of the element name so that it ends with IDE. So instead of a chlorine ion, it's a chloride ion. So remember that when you have negative ions, they end with IDE. But metals just use their regular element name. So here's a whole bunch of negative ions that we could see. All of these are nonmetals, so if they gain electrons, then their name changes slightly to have an IDE ending. So, ion reactivity. We're going to focus on the first couple groups of the metals and the last couple of groups of the nonmetals. So at this point, we have reviewed that metals generally lose electrons to become ions, and nonmetals gain to fill up their valence shell of electrons and become ions. So reactivity has a lot to do with trends, which we looked at in the previous lesson. So if you think that the thing that makes atoms reactive is how easily they can lose or gain electrons, then we can apply the trends to that and get a good idea of how reactive something will be. So if there's a tight hold on the valence electrons, it's not likely that they're going to be able to leave, right? But if there's a weak hold on the valence electrons, there's a much higher likelihood that it'll be able to be pulled off, and that would make that atom more reactive. So the idea is the further the valence electron is from the positive nucleus, it's not held as tightly. It doesn't have that positive charge pulling on it as tightly because it's farther away. So that electron is more easily removed, and that means that atom is more reactive. And so the trend for reactivity is basically the same as the trend for atomic radius. Reactivity for cations increases as you move down the table. So these are all your group 1 metals. And so reactivity goes up this way. Cesium, the most reactive, and then rubidium a little less, potassium a little less, and so on. If you watched that video I linked a few days ago of Brainiac putting these metals in the bathtub, you'll know that some are more reactive than others. And so this is the explanation for that. So reactivity increases as we move down the table. And you can see the valence electron here is much closer to the center for lithium, gets farther away for sodium, gets farther away for potassium. So it's being held less tightly. It's more easily able to leave, which is what a chemical reaction is all about, electrons moving around. And so there's your answer for why reactivity increases. We've already answered that just now, so we'll keep going. Now let's look at the negative ion reactivity. So for those negative ions that are formed over on the right side of the table, reactivity generally goes down for ions as you move down the periodic table. So it's kind of the opposite as the metals. And why is that? Well, we have to think of what's going on the other side of the table. What's going on is the opposite. Those atoms want to grab electrons from other atoms, right? So they want to attract electrons so that they can fill up their valence shell. And what makes an atom have more of a pull toward its center, toward its positive nucleus? Well, you don't want to have a lot of shielding. You want to have as minimal amount of shielding as possible, which happens higher up on the table, right? Because there's less rings. You also want to have the highest possible ZF, the effective nuclear charge. And that happens as you move towards the right of the table. So the further right you go and the further up you go is going to make the strongest pull from electrons outside the atom to join that atom. And that will then make the negative ion. So as we go up and to the right, we have a higher reactivity. So that means fluorine is the most reactive nonmetal. And as you go down group 17 or group 16, it gets less reactive. And that's the explanation. So there's our answer there. Higher up, we have less shell, so there's less shielding, and electrons are closer to the nucleus, and we have a higher ZF as we go from left to right on the table too. So that's why, say, fluorine is more reactive than oxygen. They're on the same row. They're in the second row of the table, but fluorine is one more element to the right, so it has a stronger effective nuclear charge than oxygen does. So that brings us to the end of the previous content before we really move into the new 11 chemistry stuff, and hopefully this was useful for refreshing on the concept of ions and reactivity. But if you have any more questions, just let me know. Send me a message anytime, and see you in the next video for the second part of lesson 1.4.